Alright, so in this example problem, we're given that we have a 10 kilogram lamp that is suspended from 3 equal length cords. So these 3 cords are, I'll call this point O at our origin, would be OA, OC, and OB. Alright, so we're asked to determine what is the smallest vertical distance S from the ceiling if the max force in any cord is not to exceed 50 newtons. All right. So we're looking for S, that's our unknown. All right. That we're trying to solve for. So first thing we're going to do, we'll draw a free body diagram. All right. So we're going to draw a free body diagram at the origin. All right. So first things first, we'll define our coordinate system. Alright, so we'll have our x-axis, our y-axis, and our z-axis. Alright, the next thing we're going to do is we're going to apply our known forces. So in this case, we have a 10 kilogram lamp. So we'll define that as our force W. Alright, and then we have, and that's going to go along the z-axis, the negative z-axis. And then we have 3 additional forces. We have a force that goes from the origin to point C. Alright, and let me redraw that. Alright, we have a force that goes from the origin to point B. And we have a force that goes from the origin to point A. Okay. Alright, so there's no other forces that are being applied to this system. So what we can say is that our resultant force is equal to the sum of all these forces. So it would be equal to FA plus FB plus FC plus our weight. Alright, and that has to be equal to 0. So first thing we're going to do is we're going to define, the next thing we're going to do is we're going to define FA, FB, C, F, and W in terms of, we're going to write them in Cartesian form. Okay, so we'll first start off with FA. Okay, so we're going to write FA based off of how it's drawn. We'll have an x component. We'll call that FAX plus I plus its y component FAY plus its z component FAZ. All right, in a similar fashion, the force that goes from the origin to point B will have an x component. It'll have a y component, and it'll have a z component. F of C, since point C lies along the same plane as the y-axis, it will not have an x component. So it'll be equal to 0 in x plus FCY J plus FCZ. Okay. All right. And then our last force is our weight. W. So our weight W is going to just be equal to 0 in the x and the y, and then it'll be equal to minus 9.81 meters per second squared times the 10 kilogram mass, K, which is equal to minus 98.1 newtons. Okay, all right. So what we are going to do now is we're going to make an assumption based off of the original diagram. All right. So all the chords are equally spaced, so you can see that they're all at 120 degree angles, and the the cable or the weight that's hanging from the origin point, that's going to be equal to that's the only other applied force that's on the system. So since the only other applied force on the system only has a z component, we can say that the sum of the forces in the x direction, the sum of the forces in the y direction, due to the cables OA, OB, and OC, are going to cancel all each other out. So what we can assume is from, and you could prove this using the sum of the forces in the x direction is 0, and the sum of the forces in the y direction must be equal to 0 for equilibrium to exist. Because of those two assumptions, what we can say is that the magnitude of force A is going to equal to the magnitude of force B, which is going to be equal to the magnitude of force C. All right, so that simplification will make our problem a lot simple. So because of that, we can say that what we end up getting is if we sum up all of our forces in the z direction, what we can say is that if we sum all of our forces in z and set that equal to 0, since FA, FB, C, we can say that we would say that FAZ is equal to FBZ, which is equal to FC of Z. All right. So what we can say is that we'll say that we have the same thing as 3 FCZ, all right, minus 98.1 newtons is going to be equal to 0. All right. So we can solve for FCZ as going to be equal to 3 divided 98.1 divided by 3, which should be I think 32.9 or 32.7, yeah, 32.7 newtons. Okay, and then what we're going to do is we're going to draw our so this is going to be our free body diagram of just the cable AC or OC. So this is going to be FOC. All right, this is going to be, or I should say FC. Sorry. FC. All right. We know that FCZ is equal to W over 3. So the only thing we need, what we are looking for here in this problem, is we're looking for our triangle that goes from the origin to point D from point D to point C. We're looking for this angle, theta, so we can solve for S. Okay, so this angle theta we can solve for all right using let's see here. So we were given in the original problem statement that FC, or the maximum force in any of the cables, would be equal to 50 newtons. So we were given the magnitude of our forces. So what we could do is we could use the cosine function. So we could set that cosine theta of this triangle here would be equal to the weight over 3, or 32.7 newtons divided by 50 newtons. All right, so then we can think of theta would be equal to 49.156 degrees. All right, then we can go back to our equation here, and we know that the length from point C to point D is equal to the radius of that circle. So we can set we can solve for s using the tangent function. So we know that the tangent of theta would be equal to 600 millimeters divided by s. So we say s would be equal to 600 millimeters divided by the tangent of 49.156 degrees. So s is going to be equal to 518.71 millimeters, or approximately 519 millimeters. Right. So to recap this problem, alright, we first drew our free body diagram at the origin point where all of our forces connected. We then defined all of our forces using Cartesian coordinates, or Cartesian vectors. We then found, by looking at the problem, what we noticed is that only FAC, FB, and FC had x and y components, so there was no known forces that were being applied. And since the cables were equally spread out, we could say that the magnitudes of all of our forces had to be equal to each other. Therefore, all the z components of the forces would also have to be equal to each other based off of the geometry. So we could then sum all the forces in the z direction and set it equal to 0, and solve for the force z component of our force in cable C. And then we looked at the free body diagram at point at the origin point, and we were able to solve for our the angle that our cable would have to be held at using the given 50 Newton force and the z component of the weight we just solved for. Using that angle, we could then go back to the original geometry of the problem and use the tangent of that angle with the known length from point D to point C to solve for the height S.